pretty straightforward. So we're just going to work on similar things to what we did last time. Just make sure that this is recording because I don't want to lose it. Okay, so last time we talked about assigning Mulliken symmetries. We looked at some arrows and some molecular orbital diagrams. Not really diagrams, but just sort of snapshots of a molecular orbital on a molecule. We'll do some more practice. We'll do all of the ones in water. This was something you needed to do or at least look at and understand for the lab. And then at the end of the lecture notes last time, we had all the molecular orbitals for water, and we had the symmetries assigned. And so this morning we'll go through all of them. We're kind of using this Mulliken flowchart. This is not a bulletproof flowchart, but I went ahead and made it to at least try to organize your thoughts to some degree on identifying X, Y, or Z. And those kind of have priority over other symmetries. If you see a symmetry that's broken, in other words, X in the positive direction is a different color, or the arrow is pointing a different direction than the arrow in the negative X direction, then you've got broken symmetry along X. And when I say broken symmetry, it's the same on both directions. And now what is the same? Let's talk about that in terms of these arrow diagrams. So if a bond is stretching, let's just do CO2. So I'm standing here on the origin of the molecule. I'm looking both directions. This is Z because it's a linear molecule. So if that's Z, then what is this wedge one here? X, very good. And then this one is Y. So counterclockwise when you draw the coordinate system that way. And I'm standing on the origin and I look to the right and my eyes right there, and I'm looking to the right and I see this arrow pointing in that direction. So the tail of the arrow is close to me and the head of the arrow is pointing away. And I look in that Z direction and I see the arrow pointing away from me. Okay? And I take note of that. And then I look this direction and I see now the head of the arrow is closest to me and the tail is farthest away. So when I look this way, the arrow is pointing towards me. When I look that way, the arrow is pointing away from me. See, those are opposite signs in terms of Z. Okay. And so this would have Z symmetry. It's pointing along the Z axis. But when I say the same as in this flowchart, it says, is negative Z the same as minus Z? What do I mean the same as? It's from the perspective of the center of mass. Okay, so let me turn this so you can see it. So I'm standing on the center of mass. I look to the right. I see that the arrow is pointing away from me. I look to the left. I see the arrow is pointing towards me. That's a minus. That's like this arrow's been flipped, okay, from my perspective. And so also you can just look at these two arrows. They're both pointing in the same direction as Z. Okay. Let's look at this situation. I look to the right and I see an arrow going away. And then I look to the left and I see the arrow going away. So from my perspective, both arrows are going away from me. And so the left side and the right side, or positive Z and negative Z, are the same in terms of my perspective standing on the center of mass. I look to the left, I look to the right, they're both going away from me. So that would be Z squared. Z squared. Another way to think about it is think of these bond lengths. Okay, this is R1 and R2. Is R1 getting bigger? Yeah, so that's a plus. Is R1 getting bigger? That's a negative, right? It's getting smaller. What is the Z-axis over here? Positive numbers. What is Z-axis down here? Negative numbers. Positive increase in bond length, negative. Okay, so that's the same symmetry as the Z-axis. What about here? Bond length 1 is getting bigger. Bond length 2 is getting bigger. Plus and plus. How do you get plus on both sides of a Z-axis? You square it so that these negatives now become positive. So this has the same symmetry as Z squared. So again, this is deceptively simple. Let yourself get it. Okay. If both bond lengths are increasing on the Z-axis, that's like saying that the negative part of Z-axis has been squared and now it's positive. So that's the same symmetry as z squared. We're learning the symmetries of these functions rather than using them explicitly. Can you see all of that?
Yeah.
Okay. Okay, so that's kind of what I mean by is it the same as or different as. And so let's go through, let's look at the molecular orbitals in water, and we'll see how this, how comfortable you are with it. These are the ones in ammonia that we did last time. And so if given an MO picture, you should be able to assign that Mulliken notation. Probably, like I said, about 1/5 of the exam is just assigning Mulliken notations to molecular orbitals or arrow diagrams like this. These are the stretches and bends and things in a molecule. So let's go through water. And so we have all of these molecular orbitals in water, and let's go through them. So I'm looking at this molecule. If you wanted to use your Mulliken notation, your flow chart, you can look at this. Here's the coordinate system up here. And here's the molecule, and we can say is the left and right. So y-axis, looking to the left and the right on the y-axis, the left is the same as the right. So that'd be y squared, not y. And the front and back, we had no indication that the front is red and the back is green. And sometimes that's the case, but not in this particular picture. We don't see any kind of green in the background or anything like that. So we would assume that the front positive x is the same as the negative x, so x squared. And then up and down the z, there's no difference in the top or the bottom. It's about slightly different shape, but we're looking at the colors. We're looking for green and red. Okay. And so what do these colors represent in the molecular orbital? Remember, it's expanding and contraction of the electron cloud, the sloshing of the electron cloud. And so this one is shrinking and expanding in all directions. So it's expanding, positive in the x and positive in the negative x, positive in the y and positive in the negative y, and positive in the z and positive in the negative z. So all those functions are squared, if you will. There are no negatives, except they all go negative together and they all go positive together. So they're the same sign. And so that would be this x squared plus y squared, or x squared, y squared, z squared. We go through, we don't see any broken symmetry in this molecule, so it's going to be top row. It's going to be symmetric everywhere. Now, it's so then that we follow that across, and that's going to be A1. So we would label this orbital A1. And we see that in this diagram down at the bottom. This bottom one's going to be A1. So let's do this one. We go positive and negative y. It's the same. Front and back, x is the same, but z is different. See the broken symmetry along z. So there's a color change as I go across the origin of the molecule or the center of mass of the molecule. And so the top is a different color than the bottom. That's really all you're looking for. And so then that would be z symmetry. So that would be A1 as well. Even though it has broken symmetry, it's broken along that symmetry axis, the C2 axis. And so that's z symmetry. It would be top row. Another way you can kind of check your work if you're still unsure is walk this orbital through the character. This only works for single dimension rows on the character table. So A and B rows are single degenerate. They're single dimension. But you could take any of those single dimension ones and look at the pictures, the colors, and walk through all the different symmetry elements. So, of course, if we did an E operation on this orbital, it would be unchanged, and so there'd be a +1 here. But if we did a C2 on it, so we rotated the molecule with its orbital 180 degrees, did the colors change? No, so you get a +1 character under that. So what we're saying is, if I take that wave function and I operate on it, what's the coefficient in front of the wave function? It's +1. If the colors swap, then it'd be a -1. Okay. If I did a reflection here in the XZ plane, so that's the one that's right here. This is the XZ plane. Let's see if I can draw it. Okay. And so that's the left and right reflecting into each other, and the color stays the same. So that's a +1. And then if I did a reflection in the YZ plane, which is the plane of the screen, the front and the back of the molecule look the same. And so that'd be a +1 in the YZ. So that's what those characters mean. If you operate on it, that's the number in front of the wave function. It's either +1 or -1. If it's a doubly degenerate row, they're coupled together. And we'd have to use the projection operator to get those. And that, again, will be in a supplemental lecture. It's not needed for this exam. So let's look at this one. The front and back of the molecule, X, is the same, but look at Y. As I go from along the Y-axis, you see the symmetry is broken along Y. I have a color change when I cross the origin. Okay, so the left and the right do not look the same. So that's Y symmetry. The top and bottom are the same color. There's no color change as I go north and south, up and down on the Z-axis. And so this would be Y symmetry, and that's B2. So it's that simple. That's all you got to do is find how the colors change. Let's do the character table on this one as well, just to show. So, of course, we did an E operation. Nothing changes, so we have a +1 in front of that wave function. But if we did a C2, notice if we did a C2 rotation, the colors would swap. And so there'd be a -1. If we did a reflection in the XZ plane, so that's this plane again that splits the molecule in half. Do you see that when I talk about the XZ plane, that's this plane right here? Do you see that? So the XZ plane is the one that comes straight out at you, and it's the left and right reflecting into each other, and that would swap the colors. So that's why we have a -1 here, right there. And then the YZ plane is the plane of the paper, and that just keeps green the same as green and red the same as red. So the front and the back of the molecule are reflecting into each other, and you don't have a color change. So it's a +1 for that YZ plane. Okay. Now notice what we've done here. This is slightly tricky. So we've got the molecule. Now look at the hydrogens. Where do the hydrogens go? They've gone 90 degrees, haven't they? We can't rotate the molecule without rotating the coordinate system. So look what's happened to the coordinate system. We go back. See, X is pointing at us, and Y is pointing over this way. And so then we rotate the molecule. I wish I could do this slowly. And now Y is going into the board, and X is in the plane. Okay. That's why when I say it's always counterclockwise, it's counterclockwise if you draw your axes like this. But if it's rotated, then it's counterclockwise if you're standing over here. Okay. So we rotated the coordinate system and the molecule.
Does it matter if you put Y forwards or backwards? Like if you do it pointing into the board or pointing out of the board, do you care? Or is it just like visualization?
I think in this case it would probably still be the same. Yeah. You would, since we're not really caring about which side is green, which side is red, because sometime later they're going to swap color, you'd get the same answers. Okay. So, but I was just showing that as we rotate the molecule, we have to rotate the coordinate system. Yeah. Now, if you drew Y coming out, then it would look like a left-handed system. So that's not cool, because we're using right-handed symmetry to go with the character table. So I would still, if we're going to rotate it, I would do it like this. Yeah. So let's stick with this one, and we'll look now the x-axis. If we had kept the molecule in its former rotation, we would see red in front and green in back. And it might be hard to see that green in back or the red in back. And so that's why I rotated it, so you could see that it changes along x. So as we go along x, you see a color change. As we go along y, you do not. And as we go along z, you do not see a color change. And so this one has x symmetry. So that's all you have to do for these, is identify x, y, or z, or some combination of those. And we'll do some combinations on the board. Okay. And so that's B1. So this orbital, molecular orbital, would be labeled B1. Okay, this one's a little more complicated orbital. It's got some nodes inside. So not all nodes are planar. You can have strange shaped nodes. And so here the s orbitals on the hydrogens are shrinking, while the sort of the 2py orbital on the oxygen is expanding, and sometime later they're swapping, they're expanding and contraction. And so looking at this, though, it's a more complicated molecular orbital, but the assignment is still the same. If I look along the y direction, it changes sign. But if I look along the x direction, it does not. I look along the z direction, it does not. Okay, and so this one is going to be y symmetry. Okay, and that's B2. And then this is just a cut through that molecule. Notice how we have the same sign in Y, front and back, and X is the same sign. But in Z, it's not much of a change, but the top is red and the bottom is green. And so going along the Z axis, we do see a change in sign. We see a change in color for this molecule. And so this would be Z symmetry. This one might be the one that tricks people, and you might get that one wrong. But just look, standing on that Z axis, I go up, I see red, I go down, I see green. So that's Z symmetry. And so that would be A1. And so this is the top, or the orbital with the most curvature. You see it changes sign the most times. It has the most number of nodes. So that's the highest energy molecular orbital. Why is it highest energy? It has the most curvature, the most change in sign, the most nodes, the most strange looking nodes too. So the more curved a wave function is, the more energy it has. Okay. And so here they are. We've done all of them in water. So these are all the molecular orbitals in water. And we've assigned their symmetries. And so now we know this one is A1 down here. This is A1. There was Z symmetry, okay? This one had Y symmetry, so that was B2. This one had X symmetry, so it was B1. This one had Y symmetry, was B2, and this one had Z symmetry, which was A1. So now that we've assigned the molecular orbitals, we could populate them. How many electrons does water have in its valence shell? So you've got, let's just do this, a dual-stop structure. So let me erase this. So I'm going to go all the way back to Gen Chem. Oxygen has how many valence electrons? 6. All right. And hydrogen's 2 of those. There's 2 electrons each, so 8 electrons total. Okay. We make the bonds between the atoms. So central atom of oxygen, 2 hydrogens. We've used 4 for the bonding. 4 electrons left. What do we do with those extra 4 electrons? We put them on the most electronegative atom. So we've used up all of our electrons. That also tells us we have 8 valence electrons to make the oxygen molecule. When we make the molecular orbitals, okay, we'll learn how to do that later in the molecular orbital section and the projection operator, etc. But we get all of these pictures. It doesn't generate any more electrons. We just have those pictures, and we start at the bottom, and we put 2 electrons in each orbital. So when we go to this point here, we have 2 electrons in each of those orbitals. So that's where the 8 electrons came from. And so then we get to this point here, we have, this is the highest occupied molecular orbital. And this is the lowest unoccupied molecular orbital. Very simple, okay? HOMO and LUMO. Just find where the electrons stop. That's the highest occupied molecular orbital. The next open spot is the LUMO, the lowest unoccupied molecular orbital. And so then the first question you're going to ask is probably, is this transition allowed? Can we go from the HOMO to LUMO transition in water? Okay, so let's do that. So the question is, And we're talking about absorption, so direct absorption of light, just a single photon. And so we have three choices. We have X polarized light, Y polarized light, and Z polarized light. So we really have three calculations to do. And so the intensity is proportional to this transition dipole moment. Squared. Really, I mean, we just need to figure out if this inside integral is going to be 0 or not. So what's the symmetry of the highest occupied molecular orbital? We go back to our diagram, we see it's B1. The symmetry of the LUMO, B2. And then light, we have three choices, X, Y, or Z. And so let's start with X, and then we do the same thing with Y, and then the same thing with Z. So let's do the X one. So in C2V, what is X symmetry? Which one? B1? Okay, so we have this B2, B1, and B1. So then we go to our direct product tables, and we look at the direct product between B1 and B1. Now, you're going to see this in the direct product table, but this is something over time you should just pick up on. Anything times itself gives top row, okay, or at least includes the top row. Yeah, so this B1 times B1 is going to give us A1. You can see that on a direct product table listing in the back of your packet of your character tables. And so then B2 times the result of this, which is B2 times A1. Now, if you'll notice also in the direct product tables, anything times A1 is returned that thing. So if I had B1 times A1, I get B1 back. Okay. So B1 times A1 or B2 times A1 gives me B2. So for X polarized light, my integral is a function that has the symmetry B2. And that's not top row. So that's going to be equal to 0. Therefore, not allowed. So X polarized light can't cause this transition to occur. So this one is equal to 0. Let's look at Y. I'm going to go ahead and erase. So in C2V, Y is equal to B2. Okay. And so then we have B2, B2, and B1. All right, B2 times B1. I don't know that one. I have to look that one up. A2. All right, and then we have B2 times A2. You look at the direct product table, B1. So this is the integral over all space of a function that has the symmetry of B1, and that's not top row. So I know that's equal to 0. Not allowed. Okay, so this one's equal to 0. One more to go. Z is equal to A1. Now remember that one because it's top row. So then we have this integral B2 times A1 times B1. So anything times A1 is itself. So B1 times A1 is B1. And then B2 times B1, we just did that when that was A2, correct? So I have the integral over all space of a function that has the symmetry A2. That's not the top row. It's A, but it's not A1. Top row is A1. So that's equal to 0. Therefore not allowed. Okay, so this one's equal to 0. And that's the way it is. We shouldn't fret. The HOMO to LUMO transition cannot be excited by direct absorption of light in water. It's a good thing, too, because that means water is transparent. Okay. If that HOMO to LUMO transition, if the energy between those two levels was in the visible region and it was allowed, water would absorb visible light. Okay. And our clouds would be a lot darker than they are. Okay. But if that transition were in the UV, it still wouldn't necessarily absorb it. It's the symmetry that tells us if it's allowed or not. But this makes light even more transparent than it would otherwise be. Because that's the first available transition is the HOMO to LUMO. We might see one that's HOMO to some higher level, and so we might be able to find one of those. In fact, let's look and we'll see. So looking here, yeah, let's look at this one, the HOMO to LUMO plus 1, the one above the LUMO. So in this particular diagram, let's look at this transition here. So an electron gets hit with light and gets bumped up to here. Is this one allowed? See, it's skipping a level. Okay. And all we need to know is the symmetries of the levels, and we can do this. So we have now B1 to A1. Can we go B1 to A1? So now we're looking at this B1 to A1, and what can go in here? Let's see if anybody is ready to just hop on this one, okay? So I'm looking at this. I need something in here that after all the multiplications is going to give me top row, okay? And what I see, before you jump on it, I see something that's broken symmetry, and I need to cancel that odd nature with something. Remember, anything times itself is A1. So I need to find light somewhere in my character table that has B1 symmetry. Is there one of those? Is there an X, Y, or Z that has B1 symmetry? Yes. Boom! What is it? X. So B1 symmetry, I know, is going to be good. So that's X symmetry. X polarized light is going to cancel or interact with this odd wave function and make it even. And then when I multiply that by the even function I'm going to, it's going to stay even. It's going to stay top row. So B1 times B1 is A1. A1 times A1 is A1. So I end up with the integral over all space of an even function. And that's not equal to 0, therefore allowed. So X polarized light can come in and hit that highest occupied molecular orbital, transform its symmetry to where now it's compatible with the LUMO plus 1. And if the energy of that light matches, so you have the symmetry of light, which is X symmetry, and then you have to also match the energy difference between those levels. If the energy difference matches, the symmetry matches, then you have the probability of a transition. Yes?
Does it matter if we put the squared or not on the...
Really, no, because we're just talking about non-zero, so it'll be non-zero and then you square it. So that'll give us the intensity. But with symmetry, we're not calculating the absolute intensity. We would do that in next week in the numerical, like using Gaussian, and it would actually calculate what's called the oscillator strength, the the intensity of that transition.
So we don't have to put it for the notation.
We don't really have to put it for the notation because we're really just working with what's inside the integral to decide whether the integral is going to be 0 or not. And so if it is 0, it's 0 squared. If it's non-zero, it's something non-zero squared. And if it's negative, which we can't tell from the symmetries, it might be negative, but when we square it, it becomes positive. Yeah. So yeah, whether the square is there or not, I wouldn't even notice. I'd be focusing on your symmetry. Yeah. Awesome. Let's do some arrow diagrams, and let's pick some strange ones. So I'm just probably going to stay on the board here. Let's draw some molecules. Let's do I want something with fourfold symmetry. So let's do ethene, okay? So C2H4 ethene. In doing the Lewis-Dot formula, we ended up with, you make single bonds, you use 2, 4, 6, 8, 10 electrons, and you have 2 more left over. And it doesn't make sense to put a lone pair on this carbon or that carbon, because carbon, nitrogen, oxygen, fluorine want 8 electrons, and they will double bond to get them. Okay, and so then we end up with this carbon having 8, because it's sharing 4 pairs, and this carbon having 8. So we form that double bond, and we make ethene. Now the shape of the molecule we get from the Vesper theory, the valence shell, electron pair, repulsion theory. So these are domains, and there's 3 electron domains around this carbon. So what do we call that structure around this carbon? Trigonal planar. Yeah, trigonal planar, and it's sp, how many P's? Yeah, so how do we get to the sp2 versus sp3? Hopefully that doesn't confuse you, but think about it. It's got 3 electron domains. It's going to form the hybrids. It needs 3 hybridized orbitals. You always start with an S. It just needs 2 more. So sp2. So these are the p orbitals. So sp2, and you get your 3 electron domains. What about the double bond here? Well, that's using that unused p orbital, the pz orbital. Okay, that's kind of telling you that the z-axis is coming out of the board. Okay. So we're going to draw this coordinate system like this. Z is coming out of the board, and so then that means this is X, and that's Y. This one is tricky to assign the Z-axis because we have a C2 axis coming out of the board. We have a C2 here and a C2 there. It's D, what? What is the symmetry of this one? D2H. So that's the point group for this molecule. It's D because you find the C2 axis and there are 2 perpendicular C2s. And so that's what throws you over into the D groups, and meaning D2H, D2D, or D2. So it's one of those 3 point groups. And because it has that horizontal plane, then it's D2H. Now what if you had chosen this one as your C axis that was the highest order in? See, they're all 3 C2 axes, and so that's the real ambiguity for this molecule, is which one is the principal symmetry axis. And the convention is when you're having these double bonds, we call those the PZ orbitals, the unused PZ orbitals, and so that's kind of telling you this is the Z axis coming out of the plane of the board. Okay. So that's a lot about ethene. So let's now look at this molecule. And let's draw some CH stretches on here. So I'll put some arrows. If we have these bonds increasing, while these are shrinking, we look at those arrows. We could stand on the center mass. We could We could look in the X direction and we say, wow, the arrows are going away from me. And we look in the minus X direction, oh, the arrows are coming towards me. Okay, then the negative X looks different than the positive X. So it have X symmetry. If I look up in a Y direction, I say, oh, I've got an arrow going away and an arrow coming down. And then I look down, oh, I've got an arrow going away and an arrow coming at me. That's the same, whether I look up or down. So it'd be Y squared, it wouldn't be Y. And then I look in the Z, I don't see any arrows at all because they're in the XY plane. Okay, so the front is the same as the back. So you see that the symmetry is broken in the X direction. So this would have X symmetry. That's one way to do it. What's another way to do it? What's another way to find the whether it's X, Y, or Z? The components, yeah. So if we look at this, the X components do not cancel, but the Y components do. They're going away from the Y-axis. You know, they're going up and down. So the up and down part would cancel, but the left and right part does not cancel. And so there would be X symmetry. So what's in this molecule? What is the Mulliken notation for this mode? So find D2H in your character tables. And hopefully that's one I've included. It's on the front page, yeah. Did you find it? So you go over on the right, you see X way at the bottom, you come across, it's B3U. What's that U stand for? I don't think I've ever used the word this semester, okay? It's talking about inversion symmetry, and it's even or odd. We use that term a lot, but we've used even and odd so many times. Let's just, instead of picking like Greek characters, let's pick another language. I don't know, German, okay? Just out of a hat, right? So this is ungerade, which is uneven. Gerade is even, yeah. G is even, and ungerade is uneven. Yeah, so the U and the G tell us under the inversion column, if you look up there under I, you see plus ones on the top half of the table and minus ones on the bottom half of the table. The top half of the table is G's, and the bottom half of the table are U's. And so it's just talking about inversion symmetry, gerade on top, ungerade on bottom. So you can learn all kinds of things, in Greek, alpha, beta, gamma, and then gerade and ungerade. You can learn some German. Okay. Yes. So, as if chemistry wasn't part of that. So then this is our vibrational symmetry. Okay. Just get this up. And what do we know about vibrational modes, right? They alternate. A1, or top row, this will be A1G. So let's just draw that. The vibrational potential. So if the molecule is vibrating around zero, you know, these bonds stretch and compress, and then sometimes they go back the other way along the x-axis. And we have these energy levels. So it goes A1G, B3U, A1G. So it alternates. So we know if we're in the ground state vibrational vibrational level for this molecule, it's A1G, and the first excited state is B3U. So if we wanted to know if this was excitable by light, we would have this B3U here and A1G here. And so what do you think is going to go here in the middle to get this thing to be A1G, top row? Yeah, we need something identical to this to cancel out the broken symmetry. So we need B3U here, and that is X symmetry. And so if the vibration is X symmetry, we need X polarized light to excite it. And that's why that column in the other character tables where I said IR, you know, if the mode was B3U, it was X symmetry, then light of X symmetry will also excite that vibrational motion. Okay. And so then let's go ahead and do this. Anything times A1G is that thing. So B3 times A1 is B3, and Ungerada times Gerada is Ungerada. So U times G is U, and then we have this canceling out. B3 times B3 is A1, and then Ungerada times Ungerada, U times U, odd times odd, gives even. And so we get an integral over all space of a function that is top row symmetry, which is not equal to 0, therefore allowed. And for bonus work, if you wanted to put some more stuff on your pages, you could show that Y symmetry would not be allowed and Z symmetry would not be allowed. So if you want to do that just for grins, just prove to yourself that only X polarized light would be able to excite this vibrational mode. Yes?
Is there like a difference between A1G and AG?
A different point group. Yeah. Yeah, so that you would. Oh, did I have? Okay, I've been putting A1s. I was just going on memory, so my memory was bad. It's just AG in this particular character table. So sorry for confusing the matter. In some molecules, you have A1 and A2 with Gerada and Ungerada. So in D6H, so for benzene, that's on the next page. Because you have A1s and A2s, you have to distinguish between them two. So that's kind of in my mind what I was thinking. I didn't realize that in D2H you didn't have the 1s and 2s. You just have A. Yes.
So the D2H character table, AG is your top row, so everything is allowed.
If the triple product
Yes.
has that top row. Yeah.
So, but A is not, since it's not the top row.
Correct. It has to be top row. Anything else is odd.
Okay, so the G and U's are pretty important then.
Very important, yeah. And not only that, you could look at this and let's say just if you're looking at this triple direct product and you only see one U. So like if this was a G here, you wouldn't need the direct product table. You could just say G times G is G, and then G times U is U, can't be top row, because the end is a U. But you would need to tell me that that's exactly what you're doing. Like if that's one of your answers on the test, you would say, look, just by GU symmetry, this can't be allowed. Because I know I'm going to get a U, and U can't be top row. Everybody catch that? U cannot be in the top row. Top row is symmetric under everything, including inversion. So when I invert the molecule, if it's top row, then I get the positive, a +1. So symmetric under inversion, symmetric under rotation, symmetric under every reflection. So that's why the sort of the lowest energy level is top row, because it's got 0 nodes. And if something has 0 nodes, no matter how I rotate it or reflect it, I get all +1s back. Make sense? Yeah. But if I have an inversion symmetry that's negative, then it can't be top row. That's Ungerada, or it's some other thing in a different molecule. Let's do one that's strange. Okay, I know we don't have much time, but let's look at XZ. What if my arrows were like this? Because this is the one that freaks people out. This bond length's expanding, getting bigger. That one's shrinking. This one's getting bigger. That one's shrinking. It looks like everything cancels out, but if I'm looking at this, this is plus, minus, plus, minus. So if I'm looking at X, they change shape. If I look at Y, they change shape. But look at this pattern, plus, minus, plus, minus. If I'm looking at the XY coordinate system and I multiply X times Y, I get this same pattern. That is a pattern I want you to recognize. When you have the 4 quadrants of a Cartesian system, listen to my words, 4 quadrants of a Cartesian system, and you have this plus, minus pattern, That is those two axes multiplied by each other. F is equal to x times y. X times y in this quadrant is positive. Negative x times positive y is negative numbers. Negative x times negative y is positive numbers. And negative y times positive x are negative numbers. So we see that mathematical pattern of this kind of function, xy symmetry. When I see his pattern of stretching bond, shrinking bond, stretching bond, shrinking bond, and I look at the coordinates that go with that, I look in the character table and I find x times y. Yeah, so you find x times y, and that's B1G. B1G. That's a tricky one, okay? But it's not that bad. But again, we're dealing with recognition of functions. It's a different way to do math. Okay. And so practice on that one. If you want to show them, try to figure out any kind of light that will cause this to be excited. Okay? And you can do that in your pages too. Yeah.
That's all.